Okay, so what we want to do here is we want to find the density of a cube. Okay, and then we want to compare our measured density to a literature value. Okay, so lit value, a value that is accepted in the science community. So we're given this information right here. Let's just draw ourselves a little cube to work with. Okay. Up there. There we go. Okay. All right, so we've got measurements, and those measurements include a variance or uncertainty on them. So the first thing you're going to consider is what type of tool this was used to get these measurements. And if you look, okay, if these are in centimeters, there's a centimeter division, there's your millimeter division, and then there's a tenth of a millimeter division. So this was probably done with a regular millimeter ruler with this last digit being estimated. So for significant digits, each of these has 3 significant digits in its value. But since this is an estimated digit, we have some uncertainty attached. So the first step is let's find a volume. And for that, we're just going to use the raw or the actual uncertainties and ignore this for a second. Okay, so essentially 6.05 centimeters, 6.04 centimeters, and 6.07 centimeters. And your calculator gives you a value that looks like this. 221.80994 centimeters cubed. Okay, so obviously there's too many significant digits on here. We cannot know down to the nearest, hundreds, thousandths, 10,000ths, 100,000ths of a centimeter. It doesn't make any sense. Our centimeter ruler cannot even give us anywhere near this kind of precision. Okay, so we need to look here, and we're going to need to round this. Now I'm going to hang on to this number because after we find the volume, we're going to have to find the density. And if we're looking for density, we're going to have to do another operation here, right? Because it's mass per unit volume, so we're going to divide the mass out by this. But we're going to use this whole value, and then we're going to round after. So if we're just looking for volume, okay, this number needs to be rounded out to 3 significant digits. Each of these has 3, so we got to round to here. We look at this number to be our rounding value. You get 222 cubic centimeters. Now there's variance on here, right? So we need to do this plus or minus. So how you do that is you find the percent uncertainty for each of these and you add those percent uncertainties, okay? So I'll just do the first one as an example here. The percent uncertainty is take the uncertainty, divide it by the actual value, and turn it into a percentage by multiplying by 100. So we get roughly about 0.826. And there's a little bit more on there, 4, etc. Okay, percent. And that's plus or minus on that value, okay? So what we'll do is we'll take the percents from each of these and we'll sum them. So the first one, the first percent is 0.82645. I'll just calculate out the other ones and then put them in here for addition. Okay, so we just converted the plus or minus 0.05 centimeters in each case to a percentage. So now what we'll do is we'll just add up only the percentages. Add these up together. So when I add that, I get about 2.477987%. Okay, so we've got this rounded to the correct number of sig figs. All right, so 222 centimeters cubed, plus or minus. Now have a look at this number. It says 2.4%, 2.5%. We'll round this to 3 sigs, so it matches the same number of sig figs that we have here. Since it's in a percentage, that's fine to do. Okay, you can kind of leave that like that for now. All right, and And that is the correct like propagated uncertainty for the volume only. All right. Now, again, remember when I'm finding my density, which is the end result, I use undiluted numbers, unrounded numbers, because if I keep using rounded numbers in equations, right, information starts to be missed, right, and I end up with a less precise answer than I could have. So we don't use this. This would be if we were coming to the end here, right, which we're not. We're going to actually find the density. Now, what I can also do if I'm looking for volume, and what often you'll have to do, is we have to now return this to an absolute value for uncertainty, right? So there's 2.48% uncertainty on this. Well, what is that in cubic centimeters? So in order to figure that out, 222, okay, times 2.48%, which is 2.481 hundredths. This will tell us the plus or minus in terms of cubic centimeters. So you get about 5.5. So then how are you going to write this for its final value? It's 5.5056 actually, is you're going to have the same number of smallest digits here that you have there. So there's only, a ones place here is the smallest value you can have. So you go to a ones place here. That's a 5 with something following it. So it goes up to 6 centimeters cubed. Okay. So from our initial input values, this is as precise a measurement as I can make for volume. Okay, I cannot make it any more precise than that. Now we're going to go ahead and we're going to deal with finding the density correctly. Okay, so now we want to do density, okay? Changed colors. So now we want to do density. So what are we going to do? Well, the first thing is you have to know what density is, and density is mass per unit volume, and it can be measured in one of two ways. Either grams per cubic centimeter, or that can be converted into kilograms per cubic meter. These are the two common units that we look for density in. Quite often, because chemistry influences what we do a little bit, this is sort of the more common one, and really probably more useful at the end of the day. Although if you do a conversion, something interesting happens if you convert one to the other, but I'll let you kind of figure that out on your own. So mass per unit volume. All right, so we want mass on top of the equation, right? So density is equal to mass over volume. So let's put our mass in. Our mass is 1978.55 plus or minus 0.01 grams. And then our volume is going to be found like we did before. Okay. Now the reason I'm writing it like this is because we're not going to use that rounded, and these are all plus or minus 0.05, right? Okay. We're not going to use this rounded value directly in here for volume. All right, because again, it's rounded. So we're going to use raw numbers in here, and we're going to see what we get. Okay, so going ahead and putting that in the TI-83, you get a density value of 8.92, and I put all the numbers in here, 0.02405.3. Okay, units, of course, grams and centimeters cubed. Grams per cubic centimeter, right? So you got centimeters, centimeters, centimeters. You got grams up here. Okay, now obviously that's no good. So if I look, we have 1, 2, 3, 4, 5, 6 sig figs here, but only 3 sig figs here. So this is going to have to be rounded off to 3 sig figs, so 8.92 grams per centimeter cubed. And now we just have to propagate our uncertainty. So doing exactly what we did before, except now we have a little bit of uncertainty on here. All right, we convert all these values into their appropriate percent uncertainties. We add the percent uncertainties up, and we tack it on the end of this. So just to remind you, for the grams, that's 1978.55. The uncertainty is very small, right? This must have been a pretty good scale, right? Digital scale to the nearest hundredth of a gram, right? So that's what that is indicating there. Must have been digital because this is, a 1, right? We work in a decimal system, so the assumption is that the last value is not 2, so it's probably to the nearest 100th of a gram, okay, and times 100. Okay, so I just brought in our percent uncertainties that we figured out before from these values. So the total percent uncertainty then is going to be the sum of all of these percent uncertainties. Come on, pen. Okay, so the sum is 2.47849%. Very similar to what we had before, and that is, of course, because this is such a small amount. So 8.92 plus or minus 2.48, right? We got a round here, same number of sig figs percent, and that's grams per cubic centimeter. And we're going to switch to the absolute value just to finish her off. So again, 8.92 times 2.48 over 100, 0.221216 grams per centimeter cubed. Okay, so we're going to write it 8.92, same number of decimal places, 0.22 grams per centimeter cubed. There we go. There's the density with proper propagated uncertainty, and we're essentially done with that. Okay, so now we're going to do an error analysis on this value. So we've measured ourselves in the lab this cube of unobtainium, and now we're going to do an error analysis. Okay, so let's say we go to our internet search or our CRC handbook or some trusted source of information, and you are given this. The actual true book value is 9.55 grams per centimeter cube. How do we compare and how do we decide whether this is a good value? We can't just be like, it's not good enough. I made some mistakes with my ruler. Okay, what we need is a mathematical way to decide whether this is good or not. Okay, so the first thing to look at is, if I add 0.22 to this, will this value fall within that range? And if I look, I can see that it won't. Okay, so that is an issue. But just to make sure, we're going to do this classic error analysis, which is actual minus experimental divided by actual times 100%. Okay, so what this is going to give you is what's called your percent error, or what percentage are you off by. Okay, so we're going to take the actual 9.55. Okay, we're going to minus away or subtract away your experimental, which you got as 8.92. Of course, units, grams per cubic centimeter. Okay, we're going to divide the difference by the actual value and multiply it by 100. And this will tell us our error in our value, okay, or how far away from the true value we got with our experiment. Okay, so I get an error of 6.6%. 6.6% is how far off I am, okay, from the true value. Now, if I scroll up, if you want allowable uncertainty is about 2.5%. 8.92 plus or minus 2.5%. So if this value here was 2.5% or below, I would say the reason I'm off has to do simply with random error in my measuring machine, my measuring tools. Okay, so if you are within allowable error, which in this case, that's this, right? That's what I acknowledge my tools will bring to the table. My tools will bring 2.5% uncertainty, right? So this is my allowable, if you want, uncertainty, or error, if you want, allowable error. If you're within allowable error, your technique is good. Okay? So in this case, your technique is not good. There's something wrong in your measurement, right? That cannot be explained simply by random, error in your measurement tools, okay? So in this case, we can't account for roughly about 4% of um, the error, okay? So what that means is, what we would say then as a scientist is we'd say there's got to be like some kind of systematic error going on here. Okay, and if I end up in a situation where my value is off, it's not off by much, but it's off by enough that we can't just chalk it up to, the manufacturer of the rulers, okay? There's got to be a systematic error. So it's our job to explain and suggest ways that we could improve our measurements. So one classic suggestion is possibly there's a zero error. So when we were using the scale way back here to get our input value here, 1978.55, it's possible that before we put the weight on the scale, there was already a number, negative or positive, showing on there, which happens sometimes. Sometimes you forget to zero out the scale. Okay, that's a possibility. It could have been a calibration error on the scale as well, right? If someone has calibrated that scale using incorrect methods, this value may be not, accurate, right? So the accuracy of the scale could be in question because scales have to be periodically recalibrated to known reference weights. Those are two prime candidates in a lab such as this for why you're getting a value that's outside the range, okay? What you can never say it's human error. It's human error, I can't read my tools correctly, because that's essentially what you're saying, okay? So suggestions for where this is coming from, right? You have to do this all the time in labs. You get a value outside. Once you've tested mathematically, you get a value outside. You have to figure out why that happened, or at least some primary suspects. So zero errors are very common. Calibration could be a problem. Okay, so these are possible sources of error. I guess we call these sources of error. Okay, so some sources of error that you are not allowed to use: human error. No. Okay, then you're admitting that you're a terrible scientist and you don't know how to use your tools. There's no such thing as, I didn't read the scale correctly, I can't tell what numbers were on my ruler. No, you can't say that. Okay, so that's never ever going to be in any lab you write for me. You never write human error. Okay, I will be very sad if you do. And then you're going to suggest improvements, possible improvements. So how would you improve this? Well, look at what your suggested, problems were and say, check for zero error. Go look at the scale. Is it showing a number if you still have it? If not, then a suggested improvement would be redo the lab, watching for zero errors, or recalibrate the scale. You could also possibly, if you used a real cheap ruler, you could check that ruler, check ruler against a higher quality measuring tool. Okay, maybe your rulers are off. They cost about 35 cents each, so I can't imagine they're super stringently made. Maybe that's the issue, right? What you can't say is use a more precise scale. Okay, precision isn't really the problem here, right? That scale is highly precise. It's probably not realistic that you're going to go out and get a $7,000 scale to check this value. And really, a $7,000 scale can be subject to the same problems that a $20 scale can, right? Accuracy is in how the scale's been treated and whether or not it's been calibrated and so on. It's not in the cost of the scale. I mean, a more expensive one might hold calibration longer, but it's not necessarily going to be more accurate, right? So people say, use a more precise scale. Use a more accurate scale. Not really good improvements, right? Because it doesn't explain what happened here. If you use a less precise scale, you'd have a wider window within which your value could fit, but you could still be off with it, right? Or same with a more precise one. Okay, so we'll wrap it up there, and you can refer back to this as you're doing your own labs.